Hello everyone. Our project targets to reproduce the paper RouteNet leveraging graph neural networks for network modeling and optimization in SDN. We also generated our own dataset from Mininet and ONOS to train our model. A brief summary of RouteNet is that it is a network model designed for SDN. Based on network topology and traffic data, it can predict key performance indicators of a network like delay, jitter, and packet loss. And this prediction can be used for cases such as routing optimization and planning the network in an efficient way to achieve better performance. So the overall pipeline of the paper was something like this. RouteNet takes the topology and traffic information from the data plane, and based on target policies of optimizer, it makes relevant prediction, and this prediction is then used to modify the network configurations. So the first step of our pipeline is to generate our own dataset, and for our dataset generation, we make use of the containerized version of ONOS, Mininet, ONOS CLI, and Mininet CLI. The main participants here are the ONOS and Mininet. We first wrote a Python script that creates random topologies with a fixed number of nodes and density type. After that, this script starts up the ONOS service in one container and then the Mininet service in another container. When the Mininet service starts, it creates a network using the topology generated in the initial phase and the defined traffic thread from the script. Then the script makes each pair of nodes send UDP packets generated by DITG in a certain parameterized interval to collect performance metrics. For each pair of nodes, these performance metrics are dumped in the file system, which is later used and parsed in with the machine learning model. This last step is iteratively executed n times, each for t seconds, which we set as arguments in the script. So following this simulation procedure, we generated the following metrics and collected them for training our model. We generated the graph attributes from the Mininet, the routing metrics from the path command of ONOS, and using DITG, we measured the traffic rate between each pair of nodes, average delay per packet, jitter, and number of packets dropped. Now, coming to our model, RouteNet, this is the basic structure of our model. We create an embeddings of the topology and routing information, and using some hidden states and the recurrent neural network, we finally make predictions based on those hidden states. This is the overall architecture of our pipeline. We first define some network configurations, and then using ONOS and Mininet, we ran some simulations to generate our data. This data was then fed into the RouteNet model, which then predicted some performance metrics. These performance metrics can be used to modify the network configurations to achieve better performance. Now, coming to the training of our model, our training and test dataset consisted of simulations of 14 nodes where the traffic intensity varied from 8 to 16. We trained our model with the following configurations. These are some of the training plots of MAE, MRE validation loss versus epoch while training our model. This is the performance of our test dataset for performance metrics like delay, jitter, and packet loss. We also explored a use case to find the optimal upgrade of a network using the lowest predicted delay by our network. So this is our sample 5-node topology. With the help of RouteNet, we explored which additional link placement will be the most optimal so that the overall delay of the network gets reduced. For this, we evaluated all possible source destination link placements with the minimum bandwidth and predicted the delay for each case. The one with the lowest delay will be our optimal link placement in the network. Here, we can see that according to our model, adding a link between node 0 and 3 will reduce the delay to 50%, which will improve the performance of our model. To summarize, first, We generated network performance data using ONOS and Mininet, capturing metrics like delay, jitter, and packet loss. We then trained RouteNet, a message passing neural network, to independently predict these metrics based on network topology, routing paths, and traffic data. Finally, we demonstrated how this model can be used for optimal network upgrades, reducing average delays by strategically selecting the best link placements. Thank you all.